morning, everybody. I hope you can hear me. So today I will speak about an exciting topic, which is quantum computing. And actually, what is quantum computing, why at all quantum computing, and what is it good for? So basically, quantum computing is all these devices that you see here. We'll come at the end of the talk to these devices. But what is at all a quantum computer? So quantum computer or quantum computing is a cross-technological and cross-scientific technology in the intersection of physics, computer science, and mathematics, which actually take advantage of quantum mechanics phenomena, like, for example, superposition, randomness, intrinsic randomness, and entanglement. And by being able to manipulate a single quantum system and control it very well, wants to process information. So this is the definition of quantum computing. And as you know, by classical computation, we process information through bits, that is 0 and 1s, and we get either 0 or either 1 in the response. By probabilistic computation, we fluctuate between 0 and 1s with different probability distributions, so we get fluctuation between 0 and 1s, and this is still two classical bits that fluctuate. And quantum computing, it gets actually advantage of superposition. These balls actually, they should be spheres, but this is not our quantum compression, is the compression of Google Drives when I pass the slides. And in this quantum world, the 0 and 1 is in a superposition, which it means one qubit actually can process information with different amplitudes, which is written A1 and A2 here. So these amplitudes are the probability distribution at the same time. So normally in the media, you see this presentation as a sphere, should be a sphere here, or it is the Bloch sphere, or the famous Schrödinger cat, when you say that the cat is dead and alive, which is a wrong language because the cat is in a superposition of, has the probability of being dead and alive at the same time. So this is what we leverage for processing information. So now if you add 2 qubits or more classical bits, as you see, you get a certain advantage because in the classical way of computation, you will encode your information in a bit strings, and you actually will have 1 out of 2 to the n possible permutation. In the quantum computation, through the superposition, you will get all the possible superposition states 2 to the n processed at the same time. So now the question is, but if I actually put these things in the superposition, then what I have? I just have n qubit linearly adding up. And then I go to probabilistic classical computation, which everybody is confusing what is better, quantum or probabilistic. So this will not give you anything, basically. What you want to do, you want to entangle these qubits. So this is the power. You actually process the information in an entangled superposition state, and this entanglement is nothing else as a kind of computational multiplier of all these qubits that live in this space in such a way, actually, that you will get an exponential, you will process the information, and you might get an exponential speed up in comparison with if you get just linear classical qubits and add them one to the another. And this is this famous entanglement, and this is what Einstein didn't accepting and say this is a spooky action at the distance. We are not going to explain physics now, just to give you that this is the crucial part, this entanglement, because the input state is in an entangled superposition of all these qubits, and this gives this exponential advantage. So this is our quantum computer. This is all. We have all the possible probability space, and we process the information in this infinite probability space, and basically we want to leverage some advantage. But we humans, we cannot actually understand anything from this probabilistic space. It even lives in a kind of Hilbert space which we cannot even understand. So we are classical, we want to see an output. So we need to measure. At the moment that we measure from all the probability space, we actually get one n-bit string output, which is randomly sampled from all our possible probabilistic way of processing the information. And now you will tell me, okay, hang on, so you did all of this just to get an n-bit string randomly sampled that probably will give you also the wrong answer. So what the heck is with this quantum computing? So there should be something more than just measuring and getting one n-bit string randomly sampled. And this something more is exactly the core of quantum computer, that it's actually the ability to program and these amplitudes in such a way that you will boost or reinforce the amplitude of the correct answer by suppressing the amplitudes of the wrong answer. And the core of this is exactly this entangled superposition that we have, what is called disruptive interference. So it's not just doing random sampling or random computation. So basically, does it work for the whole problems? Are we going basically to solve all the problems of the world? Because this is how it's solved quantum computing. And no, the answer is no. The art of quantum computation is exactly to find these classes of problems where this process of programmability takes you a kind of advantage in the computation, being it exponential or quadratic or whatever, and this is what is claimed quantum advantage, quantum supremacy, or quantum speed up. So it doesn't work for all the problems of the universe, whatever the hype that the media is selling out there. So we need to find these problems that we get a quantum advantage. So now, why quantum computing? This is all what was quantum computing, nothing more, yeah? So now, why actually we need this quantum computer and what is it good for? So the first reason is hardware reason. So as was said previously, we know that the Moore law is becoming very difficult and expensive, and we want to boost the power and the performance of computation, and we are coming to a kind of threshold limit, yeah? So basically, by squeezing more and more transistor in a small space, we end up in a case that quantum effects start interfering with our electronics. So we basically cannot scale more and more transistor in a little space. But why actually from the beginning we wanted to put more transistors in a space? Because we said as the surface is smaller, then basically you can do computation faster, because if something is smaller, then you can do faster computation. But then we ended up that we forgot about the leakage of the voltage. Sorry, guys. So we forgot about the leakage of the voltage, and we ended up with a power wall where we cannot do higher frequency. From 2006, we are around 4 to 6 gigahertz, and we cannot speed up this computation. Even if we go to parallel computation, we are actually in the limit of how fast can we go with the performances. And this is synchronization. This has its own problems, all the parallelization. So a study showed that there are different ways in order to scale up, to push our performances and power, and one of these ways is quantum that sits over here. There are other ways to do it, and quantum computing is one of the ways. So this is one of the reasons, is hardware reason. The second is, as you see, computation complexity. So what I show here is, if I have 63 qubits, they are, in comparison with bits, are like 10 to the 18 bits. It's missing a power 18 here. They need 1 exabyte of memory in comparison with classical computation, and I need 100 years to run a computation in a classical world when I have only 63 qubits in the quantum computing. And if I go to 1,000 qubits, I actually end up with this time to run computation when the age of the universe is 30 billion years, it's 10 to the 10. So this is the second reason why the world is thrown in this quantum computation. And from the same reason of computation complexity is actually the time and space that is required to solve a problem. Basically, it was shown that there exists some faster quantum algorithms that can solve problems that are not solvable in the classical computer. So this cycle here, it's called P-complexity classes, means here lies all the problems that you can solve in a classical computer in a polynomial time. Polynomial time means the time that is normal to solve a problem, not the time of the universe, or that the problem doesn't scale exponentially with the input as you increase the input data set. So then they were found that we can have some quantum algorithms that can solve problems that lie outside of this cycle, and this gives kind of a kind of boost. Let's try to build such a computer because we might discover more problems that they are hard for classical computation and solve them in a quantum computer. So a second reason is a specific simulation, unique simulation that the native language of these simulations is quantum, for example, quantum chemistry. You can simulate them classically, but you cut all the correlations and you cut many, many things. And exactly this managing this complexity gave birth to these algorithms, and let's go who were these algorithms. Like the first one was a Shor algorithm, which actually showed an exponential speed up in order to factorize a large prime number. And factorization of a large prime number actually gives you the threats to the existing internet security, which is asymmetric encryption. The same, we have the D-log algorithm that is also showed Peter Shor. It's a show an exponential speed up, which also is a threat for the cybersecurity. And there was a Grover algorithm that has a quadratic speed up that actually it's a brute force attack for the symmetric encryption. So from all of this, it was a reason to build a quantum computer. But one reason that is never spoken is the energy as a computational resources. Because actually what Landau said that information is physical, which it means each time that you do a computation in an irreversible way, which some of our logical gates, they are irreversible, then you actually dissipate energy. And by this, every time that you erase one bit in your logical computation, you dissipate energy. And this is the Landau limit, how far we can go with the energy dissipation. This is some targeted systems to get close to this Landau limit, and this is all our benchmark systems that we work now. And by 2000, okay, let's take it 14, we see that the energy that we need for computation actually exceeds the world's energy production. And then what you do with it? Or you change all your computation to reversible logics, that you can do it classically, or you find a computation that processes the information in a reversible way. And quantum computing is a reversible way of computation because Schrödinger's equations, they are reversible in itself. So this is the third reason why the world is drawn towards this quantum computation. And the difference now that why quantum computing is different also from classical is that physically we don't have only silicon and transistors. There are many ways to build quantum computers. There are artificial atoms, so superconducting circuit. There are atom, ion, molecules. We have photons, light. We can build quantum computers with light or some topological quantum computers. Another difference is that we have different computational models. We don't do only gate models. We have what is called adiabatic computation. We have one-way cluster states, and we have hybrid computations where different models. Who is going to win? We still do not know. There are the quantum computer that will solve all these problems is the famous universal quantum computer that still needs a fault-tolerant technology for error correction. Because the quantum is very noisy, when it interacts with the environments, it basically gets destroyed. So this is what is holding quantum computing, the scalability. There are existing quantum computers, near the noisy intermediate quantum computers, and there are non-universal quantum computers, like adiabatic quantum computers that are, or for example, annealers that they are used for optimization problems. That is the next talk behind me with a specific use case, how they do these kind of things. And there are companies that working, everybody has adopted his own platform, physical platform, and his own way of computation. This is a very, very high-level architecture of how this quantum computer should get integrated. It's a huge effort from classical quantum physical layer and logical gates. And this is all what is the field of quantum computers. And thank you very much for your attention. Here you can see the Google or the IBM superconducting computers. Here is the annealer, this specific case optimizer, which is in the market. And here is the chip of the photonic quantum computer that might bring us millions of qubits by 2026, as it promised. Thank you very much.